Our topic for this video is solution concentration calculations. Ways to calculate and measure and quantify the concentrations of solutions. There's different ways to do it, like molarity or molality or percent solutions or parts per million, parts per billion stuff. So we're going to go through all of those different ways and we can calculate out what the concentration of a particular substance is. So the first one that happens a lot in chemistry, the one that's the chemist's unit calculation of choice, is something called molarity. So molarity is a calculation where I take the moles of solute, so that's the stuff that we're putting in the solution, and we're going to divide it by the total number of liters of solution, which might sound a little odd. We're talking about solute in solution, not solute in solvent. This isn't about putting 5 grams of table salt in with 200 milliliters of water. It's 5 grams to make 200 milliliters of solution. And the reason behind that is because even if you add something like table salt and it dissolves in water, if I've got a container of 200 milliliters of water in it, the volume is going to go up to 200 and something, but it will go up in the same way you putting rocks into a bucket of water makes the water level go up. So instead of talking about solvent volume, we talk about total solution volume after the two things have been mixed. And again, this is the predominant unit and calculation used in chemistry. So let's show an example problem here. I want to make a solution. And so we want to make a solution that is, we want to make 250 milliliters, and I want that solution to be 2 molar. So capital M equals moles per liter. And so whenever you see that capital M, you're going to think this is a number of particles per volume. And that's the other part I want us to make sure we understand, that mole is just a number of particles. So number of particles per volume. So I got this thing and it's X number of milliliters or liters or gallons big. And inside of it, I've got a bunch of particles to go along with the water, most likely water. Okay, so how can I show a two-step calculation, and we can do it other ways. There's only one step. So I've got 2 molar, and that equals 2 moles per liter. Okay, so how many actual moles do I need? Well, I only want to make 250 milliliters of solution. So this is moles per liter, but I don't want a whole liter, I want less. So I've got 2 moles per liter, and I'm going to go liters in the numerator here, milliliters in the denominator. So the liters cancel out. And then I'm going to take this 1,000 milliliters, which is what a liter is equal to, and set it up so the milliliters cancel out, which is the volume that I'm actually using. And then I do a multiplication with that and a little division, and I end up with a half a mole. So whatever my solution, in this case, it's NaCl. So I need a half a mole of NaCl. All right, well, how much is a half a mole of NaCl? I know it's half of 6.02 times 10 to the 23rd, but remember, we can't count that. What we need to do is figure out another way to do it, which is by determining the mass that 1.5 moles would be. So 1.5 moles here, and then this number is the value of Na and Cl added together from their masses on the periodic table. And so this is 1 mole of NaCl would be 58.44 grams of NaCl. So I end up with 29.22 grams. So how do I make this solution? That's going to be important. We're going to put 29.22 grams of NaCl into the container, and then we're going to fill it up to the 250 milliliter line. So it's a little bit more complicated. We're doing this in the lab. Not a lot more complicated, just a little bit more complicated. So the containers that you use to do this solution are called volumetric flasks. That's a bad drawing of a volumetric flask. And they'll have a line on them somewhere. And so in this case, let's say this one says 250 milliliters. It's actually going to say a little bit more than that. It's going to say 250 milliliters plus or minus, say, maybe 0.1. So what that means is if you correctly put the volume in this container, that the solution could be as low as 249 milliliters, and as high as 250.1 milliliters. It's that accurate that it's only a 0.2 of a milliliter differentiation from the lowest it could be to the top it could be. When we're doing this, the walls, let's say this is we're zooming in on this section right here. There's a line right here. When you're adding water to this, what's going to end up happening is the water is going to cling to the sides of the container. And because of that, it causes something called the meniscus. And so this is gauged so that the bottom of the meniscus, this curvature part, lines up on the right at that line. So this would be how you would measure using a volumetric flask, or anything for that matter, graduated cylinder. It's just super accurate with the volumetric flask. All right, so to actually answer this question, what I would say is step number one would be to get a 250 milliliter volumetric flask. Because if I want to make 250 milliliters, I need a 250 milliliter flask. Many times you won't have that exact size. So maybe you didn't have any 250s, but you found a 300. So then you could use that to make the amount of solution that you're going to need. All right, so then step two would be calculate grams NaCl needed. So we did that. We figured out that it was 29.22 grams of NaCl. And then the next step was add NaCl to flask. The next step is fill flask, I don't know, about 3/4 full of water. So the reason that we're doing that is if I let's say I put a little table salt in here in the bottom, and then I fill it up to like here, then I can take this container and I can put a lid on it and shake it and get it to dissolve. Not all things dissolve as fast as NaCl, and so this allows you to shake it up and get it to dissolve more quickly. All right, then our next step would be fill near the line. I know it sounds like not super important, but it's important. It is important. So you're going to fill near the line, so it's something like this. So maybe like right there. And then the last one is fill to the line with a dropper. Okay, so you're going to literally have like a dropper like you have in your kit, and you're going to drop droplets of water in here, and then this level is going to go up, go up, go up, go up until it gets to right where you want. The reason you're going to do this is because if you're, say, dumping with the graduated cylinder into here, invariably you're going to end up having a line like this, and you went over. You can't just put a pipette in here and pull water out, because if you do, you will be taking some of the NaCl out with you, and so you don't have the concentration that you wanted. So you just get it kind of close, and then you use a dropper to get it to right where you want. It's basically makes it more controllable, the amount of volume of water you added. Okay, so that's how we do calculations to determine, or that's how we make a solution of a particular molarity. Okay, the next unit that we've got is something called molality. It's a tiny bit different. Molality has this L in it here, and the difference is we're going to be talking about, there's supposed to be a picture here, whatever. I know it's not much of a big deal change, but a lowercase m means molality, where the uppercase m means molarity. And so then the difference is mass, sorry, not mass, got mass on the brain, moles of solute divided by mass of solution. So that is a significant difference. Before we were using volume, and now we're using mass. The bad thing about volume is it's, as you've seen from the penny lab, you drop one penny, if you drop one penny into the graduated cylinder, it doesn't move very much. You can't check to see, it's not, your measurement isn't very accurate. But if you put that penny on a scale, you can get it to 2 or 3 decimal places easily, with depending on what kind of scale you're using. The scale doesn't even have to be very expensive. So the difference here is I would use a scale and everything could be more accurate. And that's fine, but the problem is the scale is going to have to be pretty expensive if you do this. So the reason that chemists, even though molality is more accurate than molarity, it costs a lot more. It really does. So if I wanted to take this entire solution that I had here, 250 milliliters with a glass container, and put that on a scale, with the scales I have, all I'm going to see is this, air, meaning I've gone over. The scales that I have in the lab get you up to about 150 grams. So if you go above that, then the scale can't read it. And if I wanted to have a scale that could read the mass of a 250 milliliter solution in a volumetric flask, it would cost several $1,000s. And if I wanted something, this is only a quarter liter. Let's say I wanted to make a liter of solution, I'd end up spending like $10,000 to get 2 decimal places or 3 decimal places that were accurate, because scales like that are quite expensive. So the other really nice thing about molality, and a person might use molality, is it doesn't vary with temperature. So if I'm talking about molarity, erase all this stuff inside here. If I'm talking about molarity, and I've got my volume exactly where it's supposed to be, the meniscus, bottom of the meniscus is right on the line. Let's say the temperature goes up. Okay, the air conditioning in the lab breaks. Now it's up here. What I've done is I've increased the volume, but I didn't increase the concentration. So if the volume goes up like this, now I am less than 2.0 molar, because now the volume is bigger than it's supposed to be. Well, that doesn't happen on with molality, because even if the temperature goes up, the scale doesn't care. If I'm looking at a scale and the scale reads 3.01 grams and the temp goes up, this object, in this case maybe an older penny, it's still going to read 3.01 grams. But again, the bad side about the molality is the scale is expensive, going to be quite expensive. I wouldn't be sending those scales home for you guys. It would cost too much. Oh, here's the equation I was looking for. Okay, so those are less known to the general public, but percent solutions, you see those things all the time. So first, let's talk about what percentage. So if I'm talking about the percent, let's say the percent you earned on a quiz or exam or something like that, I take whatever it was that I earned divided by what I could have earned, multiplied by 100, and I get, you know, whatever my percentage is. Okay, so the way this works with solutions is I've got some mass of a solution, and I'm going to divide it by the, mass of the solute, divide it by the volume of the solution, and then multiply by 100. All right, so if a solution concentration that you guys might find would be, you can get 3% H2O2, and this is your hydrogen peroxide. You know what? I'm gonna do that one second. We're gonna do this one first. We're gonna do 0.9% mass to volume NaCl. So that's actually an important value, 0.9%. That is the concentration of table salt in your blood. It's also the concentration that IV bags have to be, because if they're more than 0.9, then you're putting a percent solution, then you're putting in too much salt, and you're going to end up having your red blood vessels do bad things. And if it's less than 0.9, same situation, your blood salt level will drop, and you'll have the same problem. You'll have problems with your red blood cells. Either water will go into them because of osmosis or out of them because of osmosis, depending on the concentration. If all of a sudden your bloodstream is too concentrated with table salt, the water in your red blood cells will come out, and then they'll look like what a balloon would look like if you stuffed some Legos inside of it and then sucked all the air out. You'd be able to see the stuff that's on the inside, like cell organelles. And then if the solution isn't concentrated enough with salt, then the water is going to go from the blood serum into the red blood cells and possibly cause the red blood cells to pop, which would obviously be bad for you. Okay, so this here is mass and volume. This is mass and volume. So if you see this, mass divided by volume written after the 0.9. That meant that they took a solid solute and put it in with a liquid solvent. And that would be the case with table salt. Okay. We could do a calculation with that. Let's say I've got this 0.9% solution, and let's say that I've got a, I don't know, 500 milliliter solution. How much table salt is actually in that? All right, well, we can rearrange this. So X will be equal to 0.9 times 500 divided by 100. So that would be 4.5 grams of NaCl. So if I'm going to make this, I'm going to put 4.5 grams of NaCl into one of these IV bags and fill the IV bag up to 500 milliliters. And that's it. You're done with it. Okay, so the reason that I erased that first percentage, which was 3% volume to volume, and that was for hydrogen peroxide, because the H2O2 is a liquid and the water is a liquid. So in this case, what happens is they put they put a small amount of hydrogen peroxide in and then fill the container up with water. And that's why it's a VV, because it's volume, milliliters and milliliters. So let's say that we had a, 250 milliliters of hydrogen peroxide at 3%. So if I rearrange this, I'll get X is equal to 3 times 250 times, that looks terrible, times 250 divided by 100. Let's see, that would be 7.5 milliliters of hydrogen peroxide. So the way this works is they put 7.5 milliliters of straight hydrogen peroxide into a container, and then they would fill that container up to the 250 milliliter mark to have your solution. 3% is the maximum amount like a regular person can buy for hydrogen peroxide. Higher concentrations of hydrogen peroxide will just dissolve you. So like a 30% solution, so 10 times this concentration, instead of it just killing the microbes within a wound that you'd want it to, it would actually just kill everything that it touched. It's not good stuff. And higher concentrations, like it says on the Moodle page, dose makes the poison. So 3% hydrogen peroxide kills microscopic organisms and actually cells that are alive. But a 30% solution would actually just start dissolving skin. So bone, not good. And let's see what else we got here. And the last one here, we've got mass to mass. So if I wanted to be super accurate with this, I could use mass values and mass values. So this would be very similar to the way molality works. I measure the mass of both, even if one of them is a liquid, and then I would put those together. And then another way to do it is another type of solution would be an alloy. And an alloy was a mixture of 2 different metals. And then you melt them together and they turn into basically a new thing. So if I have some amount, my solute is tin, and then my solution is mostly copper. If I put those 2 things together, I'm going to make bronze. So bronze is different than both tin and copper. It's got properties of both, and it's actually a better substance than either tin or copper by themselves. And you would do this by massing out a certain amount of tin and then throwing copper in until you reach the mass that you wanted and then melting them together. All right, so the next one we're going to talk about are parts per million and parts per billion. So why would anybody care about a few parts per for every million? So an example of that is 15 parts per million lead. That's the legal limit in the United States. If your water has more than 15 parts per million lead in it, then your water is considered not potable, not drinkable. So why would that matter? I've got million water molecules and only 15 of those molecules are lead. Is that a bad thing? Well, remember, 1 swallow of water was 602. 1, 2, 3. One, two, three, 4, 5, 6, 11. There we go. So if you drink 1 swallow of water, you have this many water molecules. Okay, so that's a lot of water molecules. And we're saying for every 1 million water molecules, you have 15 lead atoms. All right, well, there we go. Let's take the million part out. And now how many lead atoms do you have in that water? You have this many per mouthful. Per swallow of water, you have that many leads going into you. So obviously that's a large number. And even though drinking water like that won't kill you immediately, it will cause problems over time. It'll end up most likely causing some sort of nerve degeneration or some kind of cancer. So I know that 15 out of a billion doesn't sound very much, but when you've, or a million, but when you've got that many, you're looking at, when you've got that many total atoms, you're still looking at a great deal of these contaminants, in this case, the lead. And then parts per million, same situation. Things that we measure for parts per million would be like the amount of sulfur that, let's say, a coal plant is generated. And the sulfur one is super interesting because you as a human are better at smelling sulfur, recognizing that sulfur is in the air, than the instrumentations that people have been able to make. So if you can't smell sulfur, then sulfur's not there. Like, that's how good your nose is. Why we would need to be so good at smelling sulfur is one of the components that happens when microscopic organisms start breaking down a dead animal. So let's say your relative from 50,000 years ago is tromping through the forest and they come across a dead squirrel. There it is right there. Sounds like lunch. Well, how do I know if I can eat that squirrel? Did it fall to its death, or how long has it been here? Like, is there a problem with it? If your relative put their nose down on that squirrel and could not smell sulfur, then that animal has not been dead so long that it's decaying on the inside. And go ahead, have at it. Squirrel soup it is. And that's the main reason for us to be able to smell things at very, very low concentrations, because we want to know that eating this squirrel is going to make me sicker than and not give me any energy, because now I have to recover from a sickness. So I need to be able to know that. And the last thing we'll talk about in this video is something called the dilution video. So we'll just start off with this equation is used to dilute things. That's it. And here's the equation. The concentration of what I'm starting with times the volume of what I'm starting with equals the concentration of what I want times the volume of what I want. So when we're doing these problems, you're always looking for this right here. You're always looking for volume 1. So the way this works for me is, let's say that I wanted to make let's say a 2.5 molar solution of hydrochloric acid. And I wanted to make 350 milliliters of this hydrochloric acid solution. All right, fine. So what I do is I go get a container that's more concentrated than that, dilute it down. So when I purchase hydrochloric acid, the hydrochloric acid comes as concentrated as the hydrochloric acid can be, is 12.1 molar. That's as concentrated as I can get. And it comes in containers that are 4.0 liters in size. All right. I am not going to be using the full 4 liters, so I don't care about that number. I want to know how much of it I'm going to use. So what I do know is I know that I want this to be 2.5 molar. I also know that I want to make 350 total milliliters. So what I need to do is divide by the concentration that I'm starting with. And when I do that, then I can get the molarities to cancel out. And let's see what I get here. 2.5 times 350 divided by 12.1. So I got 72.3. All right, milliliters. So what does that mean? That means if I take 72.3 milliliters of the 12 molar stuff and put it into a container and then fill it up with water, awesome. I'm going to have a solution that's 2.5 molar and it's 350 milliliters large. And that's it. Although if I'm talking about acid, I would put some water in first, and then I would put my 72.3 milliliters, and then I would fill up the rest of the way with water. And there's another calculation here if you want to practice with that. And that's all I have for this video. Thank you.